Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 3 on equivalent exponential expressions. The first two lessons in this unit really concentrated on looking at things that grow or decrease exponentially. But now, for the next few lessons, what we're going to be concentrating on is really the algebra of exponents. You know, what rules do exponents play by? How can we write equivalent exponential expressions in simpler ways or maybe even more complicated ways? All right, so we're going to be getting into all sorts of these things in the next 2 or 3 lessons, so let's get right into it right now. All right, exponent properties. We want to be able to manipulate expressions that involve exponents to create ones that are equivalent, right? We do this by knowing exponent properties, and we looked at some exponent properties way back in Unit 1. And so the first exponent property we're going to look at, we've already seen before in this course, and you've certainly seen it back in Math 8 and probably even Math 7, but let's tackle it a little bit right now. Exercise number 1. Write each of the following as an equivalent exponential expression with a single base. Letter A, 2 to the third times 2 to the fifth. All right, now you may already remember how to write something as an equivalent exponential expression given these types of problems. But let's review the thinking behind it, at least in letter A. Right, if we think about letter A, 2 to the third, let me write this a bit bigger, times 2 to the fifth, that literally means 2 times 2 times 2, that's 2 to the third, times 2 times 2 times 2 times, I'm going to quickly run out of space here, times 2, right? That's really what that expression means. But because multiplication is associative, right, I can group this any way I want, so I can literally remove those two parentheses, and now I can say this is 1, 2, 3, 4, 5, 6, 7, 8. This is the same as 2 to the 8th, right? So 2 to the third times 2 to the fifth is equal to 2 to the 8th, and it makes sense because there are 8 2's multiplying each other together. All right, see if you can remember then how to do B, C, and D. You can write them out like this, or you can just think about it as how many times am I multiplying X together? How many times am I multiplying 10 together? How many times am I multiplying M together? Pause the video now. All right, well, in letter B, I have X to the second times X to the 10th. Don't have a lot of room here. Let me write that a little bit bigger so you can see it. X to the second times X to the 10th. That's got to be X to the 12th, right? If I've got 2 X's multiplying 10 X's, I've got a total of 12 X's multiplying each other, X to the 12th, right? In letter C, I have 10 to the 5th times 10 to the 5th, or 10 to the 5th squared. That's an exponent within an exponent, all right? And that means I've got 10 raised to the 10th. Just like the first one, I could write it out as 10 times 10 times 10 times 10, and then 10 times 10 times 10 times 10 times 10, and then I've got 10 10's multiplying each other, so 10 to the 10th. Now finally, letter D might be a little bit trickier because I have M times M to the third, but again, that's really M times M times M times M, so that's M to the fourth, right? It's all just about how many times you're multiplying that base together. Now, this gets us to an exceptionally important exponent property, the most important property of all, letter E. X to the A times X to the B is equal to what? Well, why don't you see if you can write something down? All right, well, take a look at everything we did. 2 to the third times 2 to the fifth is 2 to the 8th, right? 3 plus 5 is 8. X to the second times X to the 10th is X to the 12th, 2 plus 10, right? 10 to the fifth times 10 to the fifth is 10 to the 10th, 5 plus 5, right? What are we doing? We're adding their exponents because it's literally telling us how many times we're multiplying by that particular base. So X to the A times X to the B is equal to X to the A plus B. All right, what an important property, right? So important it gets sort of like a whole screen to itself. This exponent property allows us to add exponents when a product exists between two expressions, and this is important, that have the same base. In other words, the base is the number sitting down here, right? It's the thing that you're actually multiplying again and again versus the powers or exponents that are up here. If that's x to the second times y to the third, there's nothing we can do. All right? If it's 3 to the 8th times 3 to the 8th times 5 to the second, there's nothing we can do. But as long as the bases are the same, when we multiply them together, we can add their exponents. This exponent property lies at the foundation of every other exponent property. Every other one is ultimately gonna come from this one. So we have to not just have this memorized, we really need to have it in our bones. We need to understand why it is, and it just flows directly from, what exponents are, right? I multiply by xa times, then I multiply by xb times, which means I multiplied by x, a plus b times. That's simple. All right, let's keep going. Let's test this property. Let's take a look at exercise number 2. Consider the expression 3 to the x plus 2 times 3 to the x minus 1. Letter A, evaluate this expression when x is equal to 4. Show your steps and give simplified answer. All right, so let's do it. I mean, it's simple enough, right? We've got this, 3 to the x plus 2 times 3 to the x minus 1. All right, I just want to figure what this is when x is 4. So, just like we do with any expression, I've got 3 times 4 plus 2 times 3, 4 minus 1. That's going to be 3 to the 6th times 3 to the 3rd. And let's actually just figure out what that is, right? I'm not going to do any exponent property there. I just substituted the x equals 4 in. So I'm going to have, let me move this over here. I've got 3 to the 6th times, times 3 raised to the 3rd, going to be large, 19,683. 19,683. All right. Now let's take a look at letter B. Use the exponent property from above to first simplify the expression and then evaluate the simplified expression at x equals 4 as well. All right. So remember, our exponent property said, back on that previous slide, that as long as the two bases are the same, we can add the exponents. Now, this property is going to work. It doesn't matter whether the bases are variables and the exponents are numbers, or the bases are numbers and the exponents are variables. It doesn't matter. The property always holds. So let's take a look at that in letter B, right? I'm going to just go to my full screen view, right? That property says that 3 times x plus 2 times 3 times x minus 1 is going to be 3 to the x plus 2 plus x minus 1. And that's going to be 3 to the 2x, right? I can add x plus x. 2 minus 1 is 1, right? So that, right, 3 to the 2x plus 1 would be the simplified version of this product when I use that exponent property, right? Exponent property said if the bases are the same, I simply leave the base alone and I add the two exponents. Notice I'm not doing like 3 times 3 and getting 9. I'm not doing that, right? I'm just getting 3 to the x plus 2 plus x minus 1. And now let's test it by putting 4 in there, right? If I now put 4 in there, I'll get 3 to the 2 times 4 plus 1. That's going to be 3 to the 8 plus 1, or 3 to the 9th. Let's take a look at that. 3 raised to the 9th is 19,683. All right. Now, the point is, right, if we're dealing with some kind of exponential modeling or something like that, and this expression comes up 3 times x plus 2 times 3 times x minus 1, it would be convenient to have it as 3 to the 2x plus 1 because this is simply an easier expression to work with than this thing, right? So we use that exponent property that says, okay, I can leave the base the way it is, 3, and just add the exponents together. All right, let's keep working. Now it's important, it is very important to become fluent with this exponent property so that you can simplify expressions involving exponents. Absolutely critical. All right, now the property itself is pretty easy to use, so let's take a look at exercise number 3. Write each of the following in simplest form by using the exponent property from above. So, for instance, letter A, 5 to the 6th times 5 to the x. Awesome. Well, again, that exponent property says as long as these two bases are the same, and they are, right, then I can write 5 to the 6th times 5 to the x as 5 to the 6 plus x. And that's a great way to leave it, or if you really want the x to be first, it could be 5 to the x plus 6. That's an or thing though. All right? Either one is completely okay. Right? As long as I'm multiplying two things that have the same base, then I can add their exponents. Why don't you go ahead and evaluate the rest of these? Not evaluate them, simplify them. My apologies. Go ahead and pause the video now. All right, simple enough. So letter B, right, we have 2 to the x plus 7 times 2 to the 4x minus 3. Because the same base, right, I can now say that that's 2 to the x plus 7 plus 4x minus 3. And now it just becomes a combining like terms thing. That's 2 to the 5x plus 4. All right. Again, really not hard. And it works regardless of whether the bases are numerical, like they are here, and the powers have variables in them, again, like we have here, or vice versa. Now, if you look at letter C, this one looks a little bit more confusing, right? We have 10 to the 2t plus 5 times 10. And it might be like, well, how do I deal with like adding exponents there? Well, keep in mind that 10 can be thought of as 10 to the first, right? And as soon as we do that, then it becomes evident that we have 10 to the 2t plus 5 plus 1, and that's going to be 10 to the 2t plus 6. All right, same thing. The final problem, right? I've got a base of 4 in each case, so 4 to the negative x plus 6 times 4 to the 7x minus 3 is going to be 4 to the negative x plus 6 plus 7x minus 3. Let's get that to actually look like a plus. And that's going to be 4 to the 6x plus 3. All right, I'm just adding those like terms in the exponent. That's it. But wow, what an amazingly important exponent property. All right, now, exponent properties are kind of interesting because you can use them in a variety of ways that can get a little tricky. Let's take a look at exercise number 4. Explain why the expression 9 times 3 to the x must be equivalent to the expression 3 to the x plus 2. Now, again, this thing's tricky, and yet, if I took some value of x, like x equals 5, and I plugged it into this expression, 9 times 3 to the x, and this expression, 3 to the x plus 2, and let me get those out here, versus somehow those two exponents, or those two expressions, are actually equivalent. You pick any value of x and you plug it into both of them, they're going to give you the same value. Why is that? Pause the video now and think about it, especially in light of the exponent rule that we've been looking at. Well, the real key here is how the number 9 relates to the number 3. If that was the number 8, or the number 2, or the number 7, there's almost nothing we could do, okay? But you see, 3 squared is equal to 9, right? 9 and 3 squared are the same number. So I could take 9 times 3 to the x and rewrite it as 3 squared times 3 to the x, and now they have the same base. And because they have the same base, I can add the exponents, and now because of the commutative property of addition, I can change that 3 to the 2 plus x into a 3 to the x plus 2. That's it. Now again, what's real key here is the fact that 9 is 3 squared. Okay, if there wasn't that kind of nice relationship between the number 9 and the number 3, there would be virtually nothing that we could do with that. All right, now the second exponent property. Wow, we just spent a lot of time on the first exponent property, and yet there's a second one that comes right from the first one. There are many properties actually that exponents have. The second one is a direct result of the first one. So let's take a look at it and make sure we understand it. Exercise number 5. Consider the expression 3 to the second, all raised to the 4th power. Letter A. Simplify this expression by rewriting it and then using the first exponent property. All right, so let's talk about what I mean by that, right? We have 3 to the second raised to the 4th. Well, anytime you have something raised to the 4th, what that means is that you are going to multiply it by itself 4 times, right? That's what it means. 3 to the second raised to the 4th is 3 to the second times 3 to the second times 3 to the second times 3 to the second. If I had cow raised to the 4th, that's cow times cow times cow times cow. I don't care what's inside of here. If it's raised to the 4th, it means that thing multiplying by itself 4 times. But now think about it. This now falls into the category of the first exponent law, right? And that's 3 to the 2 plus 2 plus 2 plus 2, or as I like to call it, 3 to the 4 times 2, or 3 to the 8th, right? So what exactly is the exponent property? When I have something raised to an exponent, and that entire quantity is raised to an exponent, that's what we want to generalize in letter B. Let's take a look at that really quick. Exponent property number 2. X to the A, all raised to the B, is equal to what? Well, again, it's really simple, right? That would be x to the a times x to the a times x to the a times x to the a, b times, and that means we've got x to the a times b, or x to the b times a. And that can be really kind of confusing, especially given the first exponent law. But it is amazing how many times you have something raised to an exponent that is then raised to another exponent. All right, and it's very critical that we kind of understand how those play. Now, actually applying that rule is very simple. Let's take a look at exercise 6. Use the second exponent property to rewrite each of the following expressions. Letter A, 2 to the 4th raised to the 7th. All right, well again, the exponent property is very clear on this. 2 to the 4th raised to the 7th is going to be 2 to the 4 times 7, and so that's going to be 2 to the 28th. I have no interest in figuring out what 2 to the 28th is. It's an enormous number. We're just going to leave it like that. All right, so what I'd like you to do is pause the video now and see if you can use that exponent property we just went over in order to simplify each expression. Now watch out. Letter C and letter D are a little bit tricky, all right? But I bet you can get them right if you think hard enough about them. Take a little bit of time now. All right, well, letter B is still straightforward. We've got x to the 9th to the 2nd, so that's going to be x to the 9 times 2, and that's going to be x to the 18th. Now for the tricky ones, right? 4 to the 5th raised to the x to the 7th. Well, we'd be tempted to just think that's 4 to the 5x plus 7, but it's actually 4 to the 5 times x plus 7. We now have to distribute that 5, very important. So that's 4, whoops. That's 4 to something completely different. That's 4 to the 5x plus 35, right? So the major mistake that a student would make in this situation is that they would only multiply the x by the 5 and not the 7 by the 5. But it's distributing, right? We have to multiply this exponent by that exponent. It doesn't matter how complicated they are. So in our final problem, right, we have 3 to the 4x plus 1 to the 3rd. So that's going to be 3 to the 3rd times 4x plus 1. We now have to distribute that, and that's going to be 3 to the 12x plus 3. That almost looks like a 2, but not quite. There we go. 3 to the 12x plus 3. All right. Really important, those last two. Make sure to understand what's going on with them. Okay, now let's take a look at number 7. Which of the following expressions would be equivalent to 8 raised to the x. 8 raised to the x. I've got choice 1, 2 to the x plus 3, choice 2, 2 to the 3x, choice 3, 4 to the 2x, and choice 4, 4 to the x plus 2. All right, what I'd like you to do is pause the video right now and think about it. You can either think about, like, if I played around with each choice, which one would get me to here, or is there a way I could manipulate the 8 to the x to get one of these choices? Think about this for a little bit. All right, well, it's all about exponents, right? So here I've got this 8 to the x, right? And one thing I should feel comfortable with is that 8 is the same as 2 to the third, right? So 2 times 2 times 2 is equal to 8. 8 is equal to 2 to the third. Therefore, I can say 8 to the x is the same as 2 to the third raised to the x, right? If 8 is equal to 2 to the third, then I can replace 8 with 2 to the third at any time I want. That's called the property of equality, right? Or the substitution property of equality. Any two things that are equal can always substitute for one another, but now I've got something raised to an exponent raised to another exponent, so this is the same as 2 to the 3x. Choice 2. Literally, you take any number, take the number 5, plug it in here, figure out what 8 to the 5th is, plug it in here, figure out what, I guess it would be 2 to the 15th is, and they're going to be the same number. Try it in any of the other ones, and they won't be. All right, let's take a look at one last consideration that is extremely important. Exponent properties work in both directions, and we should be able to use them this way. So most of the time people think, oh, yeah, I'm going to have to do like x to the a times x to the b equals x to the a plus b. But it also works the other way around. X to the a plus b is equal to x to the a times x to the b. And x to the a times b is equal to x to the a raised to the b, or x to the b raised to the a. All right, and it might seem, well, why would we ever have to do that? It's actually remarkable how often you have to go in this direction and this direction. So let's just get a tiny bit of practice with that in the last two exercises. Exercise number 8. Consider the monomial x to the 12th. Rewrite this monomial in the form of x to the a times x to the b in 3 different ways. Well, to be honest, there's an infinite number of ways to rewrite this in terms of x to the a times x to the b, but here's one for you. How about x to the 2nd times x to the 10th? Right? If I had x to the 2nd times x to the 10th, right, that would be x to the 12th, because I would add the two exponents. 2 plus 10 is 12. See if you can write it in 2 more additional ways as x to the a times x to the b. Pause the video now. Well, as long as the two exponents add up to 12, you're good to go, right? So if I had x to the 3rd times x to the 9th, I could have x to the 6th times x to the 6th. That would work. I could have x to the 4th times x to the 8th. Here's one. I could have x times x to the 11th. That would also work, right? There are lots and lots of choices there. Now that's that first exponent property. Let's take a look at the second exponent property in letter B. Rewrite the monomial in the form of x to the a raised to the b in 3 different ways. Now again, keep in mind, right, this exponent property says I would multiply the two exponents together, so now I kind of want to unmultiply them. In other words, right, I could say, well, x to the 12th is equal to x to the 2nd to the 6th. Right, not x to the 26th, x to the 2nd times x to the 6th. That is correct. See if you can now rewrite it in 2 additional ways. All right, here it gets a little bit more challenging, but it's still pretty easy. I could say x to the 12th would be, let's say, x to the 3rd raised to the 4th, and I could always flip-flop these at any point in time. X to the 12th could also be, let's say, x to the 6th to the 2nd. I could say it's equal to x to the 4th to the 3rd. All right, so there's lots of examples of where I can sort of run the rule backwards. Now, let's take a look at one last problem. Exercise number 9. Which expression below is not equivalent to 25 to the 3x plus 6? All right, well, I'd like you to pause the video now. I'd like you to look at all 4 choices, and you might want to work on each one of them kind of individually and say, well, would an exponent law justify that those two are the same? All right, pause the video now. All right, well, some of them are very straightforward, and really the one that is not equivalent is pretty straightforward. But let's just take a look at some of these. Like, for instance, choice 1, right? 25 to the 3x times 25 to the 6th. Well, our first exponent law would say that that's 25 to the 3x plus 6. So that's equivalent. Now remember, I'm looking for the one that's not equivalent. All right. Choice 2, right, says 25 to the x plus 2 to the 3rd. Well, that would be 25 to the 3 times x plus 2, right? That's our second exponent property. And that would be 25 to the 3x plus 6. All right, so that's good to go. Now let me illustrate. Choice 4 is the one that's not equivalent. Let's talk about why it's not. And then we'll go back and actually I'd like to take a look at why choice 3 still is equivalent. So choice 4 is our winner in terms of the one that doesn't work out. That's 25 to the 3rd to the x plus 6, right? That would be 25 to the 3 times x plus 6. And that would be 25 to the 3x plus 18, right? And that's not correct because I need 25 to the 3x plus 6. So honestly, choice 4 is the one that's not equivalent, okay? But I would like to take a look briefly at why 3 is equivalent, right? Because that one looks like no way, there's not even a 25 there, right? So 5 to the 6x plus 12. Well, watch this coolness, right? So if I've got 5 to the 6x plus 12, and I look at that 6x plus 12, and I look at that 3x plus 6, right? Mindful manipulation. How does 6x plus 12 relate to 3x plus 6? Well, 6x plus 12 is twice that, right? So this would be the equivalent of 5 to the 2 times 3x plus 6. But then I could run that exponent property backwards and say that's got to be 5 to the 2nd to the 3x plus 6, and that is 25 to the 3x plus 6, right? So I'm running kind of that rule backwards. I'm factoring that numerator and then taking this expression and bringing the 5 squared inside of the parentheses, leaving the 3x plus 6 outside of the parentheses, and then changing my 5 squared into what it's equivalent to, which is 25. All right. Lots of practice manipulating exponents as we move along in this unit, right? So today what we saw is we saw the 2 most important exponent laws or properties out there. One of them says when you multiply 2 quantities together that have the same base, you add their exponents together. Full stop. It doesn't matter what the 2 bases look like as long as they're the same. They could be numerical, they could be variables, but as long as they're the same, when you multiply them together, you add their exponents. The other property, which is a little bit more tricky to understand, is when you have a quantity raised to an exponent, and then that whole thing is raised to another exponent, you multiply those exponents together. Make sure you understand these 2 rules, not just memorize them, but you just have them deep inside of you because we're going to use them again and again. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.